Well, this is my pleasure to be here. I thank you very much to Karim and to the team of Karim for the organization of this school, this workshop. This is a very good opportunity to talk. I regret that I was unable to join you before, but I will stay here for the rest of the meeting in order to learn from you and to have the opportunity to discuss in details everything about biomedialization. Okay, Karim asked me to talk about biomineral as trace of life. You know, as probably you know, I was in the last trying to convince the community that morphology cannot be used as a criterion for, an ambiguous criterion for biogenicity. I mean, we want to detect life in the past. Many people suggest morphology as the main tool, actually, main proxy in some way to detect life. So in my opinion, this have several problems, and then I will try to explain you the experiment that we made in the past and that we are now also performing in order to decipher what we can do with morphology, we cannot do with morphology as a tool in order to detect life renams. So the point, as I said, this is the problem, is that morphology and texture of mineral microstructure are considered for one of the most efficient tools to detect life renams. Okay, and the rationale for this tool is that there is, people think that there is a big difference between the morphological behavior of the inorganic mineral formation and that of the living organism. Okay, and so this is something that we have in mind since centuries. Okay, that there are two different symmetry renans. Okay, and so it's very difficult to fight against this thinking, this way of thinking. Right? But in my opinion, I think that we can really show that this is not a problem between the inorganic world and the organic world. I mean, the symmetry of these two different worlds. Right? It's a problem of morphology itself. Okay, it's the same thing happening with inorganic shapes. You can have inorganic shape. Okay, both two identical inorganic morphology with very different origin. So actually, it's not a problem between the two realms of inorganic and organic world. It's a problem of the morphology. That morphology does not contain genetic information. When I say genetic, I mean morphogenesis. Okay, I don't mean actually genes. Okay. Okay. So years ago, some colleagues, when talking, I was talking about this. Okay, do you think that if you find dinosaurs, and this is the morphology of dinosaurs, doesn't tell you that this is renan of biology? Okay, and the answer is no. I mean, this is not a problem of morphology. This is not biological in origin because of the morphology. This is something that we forgot. I mean, this is already, we learned 1 century ago, thanks to a man who was working very close from here. I mean, Cuvier, the Baron de Cuvier. But the point is that, you know, this is because of comparative anatomy. This is the reason, right? Why we think and why we are sure that this is a renan of a living organism. It's not the morphology. It's not the complexity of the morphology. It's comparative anatomy. I will not go into the detail, but I think it's enough to remember you this book. This, I'm sure you know, right? The Stephen Jay Gould, excellent scientist and even better popularizer of writing of popular science. And he wrote a chapter, you know, that gives the name to this book, is Limestone of Marrakech. And you may know, in Marrakech, well, in the area of Morocco, there are people who are performing fossils, you know, and selling fossils, okay? So this paper tell about that, you know, how you can distinguish by using comparative anatomy that the fossils that the people are made are not really biological in origin, okay? So this is my point, and this is very important to realize. When we use complex morphology, okay, morphology is not the tool, it's not what tell us if something is biological in origin or not. It's comparative anatomy, okay? So the point is, when we are looking for primitive light detection, a very simple organ, is that the complexity is so small that we cannot really use comparative anatomy. And this is the point. So when people tell me, this is morphology, well, morphology is interesting, right? But really what tells us something about origin is comparative anatomy. If we have not enough complexity, it is impossible to use comparative anatomy. And this is the key point for understanding the problem of light detection at very primitive, the early organisms in our planet. Okay? So this is another thing, just for relation also with the genetic information and morphology. Is this, this is the sphere, this is the planet, this is the orange, and from the point of view of geometry, so this is the volume scale with the power of 3. So this is a Euclidean object, okay? The point is, okay, do Earth-like planets form from 3? No. Okay, morphology doesn't have information about the origin. And let me show you one thing, which is something more complex, right? Everybody knows that this is inorganic. And this is a fractal. This is a manganese fractal dendrite, and this is fractal object. Okay, so we were performing a study of the formation of these mineral dendrites. These are fractal, non-Euclidean object, very complex, right? So we measure the fractal dimensions of these dendrites. We were to the different places to find these dendrites, but also we were to the mineral shops. Okay, so and then we measured different the fractal dimension of different kind of dendrite, and it was very interesting that the dendrite that we found in the countryside, there are many different fractal dimensions, but the one in the mineral shop, all then go about 1.69. Okay, so that maybe this is let's say a gold number for fractal geometry, right? So, but the important thing is that that means that this is d equal to 1.68. This is the characteristic fractal dimension from Laplacian growth. Okay, so that we know that if you have a fractal dimension 1.68, this is something related with Laplacian growth. But the point is that Laplacian growth can be, from the point of view of physics, this is pure mathematics, okay? From the point of view of physical chemistry, we have two different ways to reach this fractal dimension and to fulfill the property of Laplacian growth, okay? And one of them is that most people think about DLA, the pyrolusite dendrite forms. This is just by diffusion limit aggregation. So you have a grow unit that move quickly and then stick with probability 1, and then if you have this mechanism, which means very high supersaturation, very fast precipitation, then you found this kind of dendrite, typical from DLA. Most people think that pyrolusite dendrite formed by this mechanism, this kind of fractal dimension 1.7, okay, this mechanism by diffusion limit aggregation, sticking probability 1. May have some water if possible. Okay, this is a random walk made by Sander, and you can see here this is the typical look of this DLA fractal. Okay, but there is another possibility to do it, and this possibility, I found this possibility in one of the cafeteria of one hotel in Sevilla. Sevilla is a very hot place, very hot place. So this was in the cafeteria. So there was windows, okay, windows with two glasses, okay. So there was two glasses window, and here is a plastic film. This is anti-crack window. This is an anti-crack window. This is how the anti-crack window look like. Okay, so you have the two glasses and then a plastic film. You can have maybe 3 glasses, yeah, but these are only 2. So what happened is that when they made the window in Sevilla, there was not very well sealed here in the lower part. Okay, so the air penetrate, And then this was looking to the sun. So the temperature here reached maybe 60 degrees. In Sevilla, this is easy. So 60 degrees is below, high. Thank you very much. So it's higher than the melting temperature of the plastic film. So the plastic film melt, and then what happens is that you have air, which is a low viscous fluid, pushing a higher fluid of higher viscosity, which is the plastic. And then when this thing happens, this is what is called the Salmon-Taylor instability. So what happens is that you create this kind of morphology, this branching, okay, that look exactly and have the same substructural dimension than the pyrolusite dry. So maybe, okay, you say, okay, this how could be applied to the formation of the mineral dendrite. Well, we made this experiment. The experiment, we have the two glasses here, and then we use here a toothpaste, because toothpaste have, some of them have quartz crystal, nanocrystal of quartz, okay? So the toothpaste here with some manganese 2 and iron 2 solution, right, in the toothpaste, okay? So we put here in a reservoir, and we fill the reservoir with oxygenated water, okay? So what we did is just with a hammer, pack, you crack the glass, and then when you crack the glass, you provoke that the fluid, the air, penetrate, oxygenate immediately the toothpaste, and then what happens is that you really form the fractured dendrite. Okay, so just to tell you that no matter the complexity, there is no information when using only morphology about the genetic mechanism. You can have information about the geometry, you can have information about the geometrical property, but not about the origin, because this is related with the physical chemistry and could be completely different way to reach morphology with equal shapes. Okay, I mean a product with equal shape. Okay, this is important. So it's not really the problem of using morphology as a way to interpret to know the real origin, the physical chemical origin of a material, is something which is conceptual or a conceptual problem. It's not a problem between the biology or the inorganic world. Okay, so here there are two different inorganic mechanisms to reach exactly the same shapes and the same products. Okay. So now the shape of minerals, because as I told you, we are trying to use mineral shapes in order to detect life, using both the general complexity of the material, but also the shape of the crystals, calcium carbonate crystal forming the materials. Okay, so crystal are shape of mineral energy, of minimal energy. Okay, the point is that why they are not spherical. Okay, why crystals have no continuous curvature? Because this is what people was thinking, about the difference between the two kind of morphology that we found in the inorganic world with calcium carbonate and in the organic world. I mean the biominerals. Well, the point is that we have this continuous curvature because crystals are anisotropic, so they have three-dimensional structure. So crystals are like that. Okay, you have a purely anisotropic material in which the property depends on the direction. So that the crystal grows. Okay, when the crystal grows, the crystal will grow with different rate depend on the different family of planes that particular for each kind of phases. Okay, so we like to use the wool plot. So it's a plot that tells you that depend on the surface energy of the different phases of a crystal, okay, you will have a final shape that is formed by the phases with minimum energy. Okay, but this is not possible to have continuous curvature for a single crystal, I mean no normal single crystal, no impurities, just a pure crystal growth problem, right? There is no way to have continuous curvature. So you always have faceted planes, okay? But, so you can have different kind of habit. Okay, the habit will depend on the different growth rate. I mean, actually the ratio of the different growth rate in a growing crystal, okay? And will depend on the combination of form of the crystal and the different in growth rate. So you can have different kind of habit, okay? But always the habit will be formed by flat faces. So that, you know, the shape of the final shape of a crystal depends, as I told you, on the relative growth rate of the faces formed in a crystal. There is I will show you just a simple case. So to show that the face that appears on a crystal, single crystal, are the faces with the lowest growth rate. Okay, so you have this initial crystal with one face, a two-dimensional crystal, one face, one O faces. Okay, both growing with the same rate, and therefore finally you have the same shape, the original shape. Okay, but now we start with the same crystal, but the growth rate of the one faces is faster than the growth rate of the one O faces. Finally, the one O faces is the only one that stay. Okay, so it is important to realize this kind of thing, that the shape of the crystal, okay, is a matter of the anisotropy, internal anisotropy of the crystal structure. So you can have variation of this, you know, different kind of let's say physical environments that change this law, which is depend on the crystal structure. So if we start to consider not the crystal structure but also the grow environment, then the thing can happen, can change. Okay, so this is a interferometric study. It's a phase shifting Mach center interferometric study. This is a drop, a drop, crystallizing drop. Okay, so you will see here now a crystal of sodium chloride, which is cubic, should have the shape of the crystal should be a cube, right? And then see that the surface saturation is higher. This is the color code. This is higher in the edge of the evaporating drop. Okay, and because the drop is that way, we have a gravity effect. So what happens is that this is the video interferometry. You will see the crystal form, okay, fall down because of the gravity, okay, and then you can see the growing phenomenon. Okay, what we have here is that because the crystal is fed, I mean the growth of the crystal fed with the solution on top, this part of the drop, you know, become less concentrated, and therefore you have a convection plume. Okay, and because the convection plume, you have different growth rate for faces with the same symmetry, with the same anisotropy. Okay, but these two faces are growing faster than this face here. Okay, so that finally what you have is a cube. It's not a cube, but you have a rectangular shape. Okay, because the growth rate depends on not only on the internal anisotropy of the crystal, right, but also on the grow environment. This is just pure physics, but I will not go to this detail. Excuse me. But as soon as you include not only the physics but the chemistry, and you look for impurities in the grow media, okay, these are, for instance, protein crystal. Protein crystal of a protein called lysozyme. It's a model protein for crystal growth. Typically, you have a prismatic phase, and then you have also pyramidal phases. Okay, if you grow this crystal, which is wonderful shapes, okay, crystal shape, flat faces. If you grow this crystal in increasing concentration of a silica solution, okay, you can see that you start to lose the influence of the internal structure, I mean the anisotropic internal structure, and you can have finally a rounded crystal, okay? Or here this is thaumatin as another protein in which you can see that you lost the influence of the internal anisotropy, and finally you have crystal which is completely rounded. Okay, so as soon as you have impurities, polymeric impurities in the system, in the growth system, okay, you can really remove the characteristic property of the crystal to have flat faces, to have rounded faces. Okay, so that silica, mimic very well what organic matter do with calcium carbonate caramelization. So these are crystals of calcite, grown from biominerals. Okay, you can see that you cannot see clearly the flat faces because of the organic matter induce the formation, the modification of the flat faces to form non-singular faces, curved faces. This is a mesocrystal, also found as a function of the, in the biominerals, as a function of the proteins involved in the biomineralization process. This is another example of the ability of the proteins and organic compound to remove the flattening of the crystal phase of calcium carbonate and to form, curved faces, non-singular faces. Okay. We also did a lot of work with Ebenezer and with the pre-pore frontiers in order to show that eggshell protein, induce the morphology of the carbonate. And this is what happened with silica. When you perform the precipitation of calcium carbonate with, in a silica-rich media, high pH, okay, in which you have the first and second deprotonation of the silicic acid, you really, induce, stop the typical, the classical growth mechanism by nucleation and spread, or by crystal dislocation, to really have nanocrystal formation. Maybe Dennis Eva told you the first day about this, right? So you have a nanocrystal formation, and then the morphology of the initial rhombohedral crystal, change dramatically. This is what we have, completely different morphologies, no more fat faces. Okay, we have this kind of growth that we don't understand yet very well. Okay, but this is a kind of growth which is mimic perfectly what happened in biomineral formation. This is another example. Okay, this is another example of just an initial rhombohedral phase that finally have these six branches that relate to the original 104 phases of the calcium carbonate. See? So we have proposed that a mechanism that, well, I think that this is not really explained because we don't know exactly how it occurred. I mean, we know that the output look like what happened in the mineral, in the biomineral world, okay, but we don't know in detail how the silica mimic. I mean, how silica is able to mimic. We know that it's able to mimic, but we don't know exactly in detail how it's able to mimic. But clearly what happened is that there is an interaction between the silica precipitation with the carbonate precipitation, and we have a coupling of this chemistry that depends specifically on pH and precisely on pH. I will tell you later about this. This is a work performed by John and co-workers. Many years ago, the people claim about the existence of nanobacteria. So these people will show. You can go to this paper in PLOS1. well, these people realized that, nanobacteria can be mimicked exactly, just by the, well, something that we already knew, right? Is that introduction of proteins, with calcium carbonate really is able to mimic perfectly everything that was published about nanobacteria, how to identify nanobacteria. Okay, I recommend you to read this paper because always this paper here, very clear. I mean, all of them related to the nanobacteria identification. Now, more complex morphology. Okay, the point everybody knows that we have a problem today with the identification of the other remnants of life in the planet. Basically because, all the criteria we were using in the past, in fact, people use each of them, only one of them as a perfect tool to identify other remnants. None of them now, are clear enough. And it's not clear that we can use isotopic signature carbonaceous remnants. This is not clear anymore. The chemical composition of the carbonaceous compounds is not clear anymore. I mean, Raman spectroscopy is not really a way to do it. We have stromatolitic light structure. I will not have time, but maybe this week we can talk about this. It is a wonderful subject. Actually, I think it's the best tool that we have right now, because it's very difficult to explain stromatolitic structure. But then the other tool that people use in morphology of pulsating microfossil, okay? Because actually, if you found in Archean rocks this kind of morphology, I mean, a structure with this kind of morphology, well, you say, okay, this is really, I mean, septation is very biological. Right? This is something that, well, look like biological. This helicoidal morphology, this also look like very biological. And actually, if I found actually something like this, so complex, say, well, this should be a proof of life, because this will be very difficult to explain this by inorganic processes. Remember the LH A411 is from Mars. The people, there was 5 different criteria to prove by NASA that they found life on Mars. One of them, that was very visual, obviously, it was a morphology of this difficult, I mean, this look non-crystalline material, right? And the point is actually that one, is that people realize that there are 2 different ways to behave in terms of symmetry, the way of life and the way of mirror, right? And they say that cannot be really, this kind of morphology can be really explained by non-biological processes. Okay, well, let's look about. This is the point. The point is that most people think, I mean, most scientists and actually most crystallographers and mineralogists think that there is 2 different realms of life. And in some way, this is, I don't know if I have here. Okay, so in some way, this is true to some way, right? Because in the realm of the crystal, okay, you have 32 symmetry point groups, 35 if you consider quasi-crystal, right? And actually, you have to fulfill this condition, right? But as I told you, this condition depends. I mean, is due to the internal anisotropy of the crystal. So in principle, right, the only possibility that we have in the inorganic world to create shapes should be restricted to this 35 point symmetry group, right? 35 if we include quasi-crystal, as I told you, right? In principle, this is true. While the realm of life is much more complex, because you can have almost every kind of symmetry. Okay, so you can have 5-fold symmetry, you can have helicoidal free symmetry, you have continuous curvature. This is the main difference between the 2 worlds: continuous curvature, no continuous curvature. Okay, but here, if you break the symmetry of the internal crystal, why? I mean, how you can do it? Well, the first thing you have to do is to split the crystal. You have to make a fibrillation. Okay, so if you split the crystal, then you break the symmetry of the the symmetry restriction of the crystallographic internal structure, and you can do many different things. Okay, I will show you how to do this. So the point is, are there abiotic precipitation mechanisms producing material with morphology that look like biological or biomineral texture? And yes, there are many ways to do it, many ways to do it. But in order to be relevant to the problem of light detection, we had to fulfill several conditions. It's 3 conditions. They must be the result of self-assembly process. Why? Because, well, I can always take a Langmuir face or just create a shape. Okay, I can create a shape with any particular morphology. Okay, and then produce the precipitation on this shaped surface. Okay, this is possible to do it, and many people doing that in material science. Okay, but this is irrelevant to the problem because we need to think something that can be performed in self-organizing way. So should be performed, 3.5 billion years ago when there was no life. Okay, so we need to have a self-organizing mechanism. So they must be fully inorganic. Okay, because if we are thinking when there was no life in the planet, then there will be not organic compounds or macromolecules related to life. So it should be something, that is fully inorganic. Because, we already know, this is what I told you before, that we can really mimic the behavior of biominerals, by using organic compounds that life produce, right? But we are talking about 3.5 billion years ago, so there was no life. So in principle, this is not relevant. So what we can do? This must be, the third one must be geochemically plausible. So we need to think in some polymeric impurities, right, that could be present in the geochemical environment of the early planet. And to me, as I told you, there's many ways to make complex shapes. Okay, I think that silica should play a very important role. Why? Because silica is rich in Earth and played a main role in the Earth chemistry before the emergence of life. So this is what I propose, is that we should pay attention to the role of silica and how silica interact with, in particular, I was studying carbonate and hydroxide, not only to produce, the talk today is about how to mimic the organic morphology, the morphology of living organisms, but also, well, maybe with relation with the chemistry and the prebiotic chemistry leading to the origin of life. So let me tell you before about what happens when you have a co-precipitation of carbonate, barium carbonate or calcium carbonate or strontium carbonate with silica rich solution, a pH between 9.5 and 11. Okay, you produce this experiment. This is very easy to do. This is an experiment where you take a solution of rich in silica with pH 11.3, and then you allow the CO2, atmospheric CO2, to go into the solution. So when you add a solution of barium chloride, of the calcium chloride, okay, or strontium chloride, an alkaline earth metal, then the final pH is about 11, okay? And then when you perform this experiment, you made a similar thing, just still to use a solution of silica, use a silica gel. And the silica gel is acidified here with hydrochloric acid, for instance, to pH 10.5, okay? And then you put on top of this the solution of the metal, alkaline earth metal, okay? And allow this to diffuse, so you found this kind of material. This is what you found, okay? And, well, this looked very biological. And actually it was a big problem for me, not now, right? But years ago, there was many people who say, you have a problem of contamination because, this is In principle, this is look very biological. I was very happy, you know. Well, not very happy because the paper was continuously rejected, but happy because okay, really look like it's not me. It's really look like biological. So the point how it works, okay. So I call this silica carbonate biomorph, and some people tell me, why you call it biomorph? Because I'm not saying that this is biological, not at all. I mean, actually, I'm just saying that they are not biological, right? But the point is that it's biomorph because look like the morphology, but just the morphology, nothing more, just the morphology, okay? And because silicon carbonate, is two key chemistry in the formation of this material. Okay, these are material which are made by. Well, they are the facts. They are made by millions of nanocrystals of the carbonate that are self-oriented one each other. Okay, so that you have orientational symmetry but not translation symmetry. Okay, and there are two phases. One phase is a silica polymeric non-crystalline phase, and the other one is nanocrystalline carbonate phase, which are, as I told you, are self-oriented one each other. These are nanocrystal with a characteristic size of 100 nanometer by 40 nanometer. In all cases, it's orthorhombic phases. So it's key here that calcite doesn't form this kind of morphology, only aragonite type structure. So strontium carbonate, barium carbonate, and calcium carbonate aragonite structure. So morphogenesis is independent of fluid dynamics. So no matter if you made this in gel, or you made it in solution, or you stir the solution 300 revolutions per minute, still you have the morphology. It's not related with fluid dynamic. And growth kinetics is controlled by reaction. I mean, it's not diffusion controlled. As I told you, only a orthorhombic carbonate create morphology with these shapes. Okay? This is just to show that when you dissolve the carbonate, okay, still you have the phantom of silica remaining, the hollow phantom of silica. You know. So there are two different routes to obtain this structure. The starting point is always a crystal of the carbonate with pseudo-hexagonal symmetry. Okay, so these have the internal structure of a single crystal, and if you maintain this, okay, nothing will happen because you will grow the crystal, and the crystal will have always a faceted shape. So it's critical to break this symmetry, and this is what the impurity, I mean the silica does. How silica does that? Well, you have the single crystal growing here, okay? So this is the case of barium carbonate. You have not only the prismatic phase, but also the bipyramidal phase. This is the bipyramidal phase is growing, and you will see what happened is that the crystal growth, because of the impurity of the silica, you know, produce the branching, the splitting of the tip of the crystal, and you have a branching which is non-crystallographic branching. It's not like a snow crystal, you know, in which you have branching to identical angles. Okay, here there is different kind of angle. It's a non-crystallographic branching, and this non-crystallographic branching, when you have repetition, no, iteration of the splitting process, you obtain a fractal structure, cauliflower-like fractal structure that look externally like globular shapes. Okay, and now what happens if you increase the pH? You increase the pH by a mechanism that we don't really know yet how it occurs. This fractal shape, you know, form two-dimensional lamella, two-dimensional laminar growth. Okay, so you have the laminar growth here. You can see this laminar growth. I think that we have better. Yeah, this laminar growth, okay, is made by this million of nanocrystal, you know, self-oriented one each other, growing radially. Okay, so if we have that kind of growth, the final shape should be a disk, right? But what happens in this kind of material is that there is a phenomenon which is the curling of the structure. I mean, the structure is growing lamellar. I mean, it's a laminar growth with radial growth, okay? And in some point, there is a curling of the structure. It's curling occurs here, here. And you will see that when the curling occurs, okay, the growth stop to, the structure stop to grow in the direction of the curling, okay? Only in the part of the structure which there is no curling, the lamella continues to grow. So what you have here is that the curling that just propagate like a surf wave, you know. So maybe you see this is what I say is that this is the curling of the structure, okay, and you will see in this video here that we just consider 3 properties of this this growth, right? The curling could be left or could be right, okay? It's chirality. So you can have the curling up or the curling down, okay? This is the radius curvature of the curling. Could be a small one or could be a very big one, okay? And these are the 3 different velocities relevant to the problem. One velocity is the velocity of the radial growth of the lamella, and the other 2 velocities are the velocity of the 2 counter-propagating curling, okay? So see what happens if we consider the growth of a disk, right? A lamellar growth, that we have 2 curling points here, okay? Counter-propagating curling points. So you obtain the way the sheaf or cardioidal-like shapes, okay? Let me show you a video showing this. This is the lamellar growth, okay? It's growing. Here are the 2 curling points, counter-propagating curling point. So one is left and the other one is right, okay? 2 up, and they are moving, okay? And they will cross here, and then you have this cardioid shape, okay? Now, exactly the same thing, but 2 up or 2 down. I mean, that means one left and the other one right, okay? So, no, sorry, one up and the other one down, okay? Both with the same chirality, left or right, okay? So you can see here, this is on focus, this is out of focus, this is up, this is down. So they are counter-propagating, okay? And then way there, you have the curvature, you have the formation of the helicoidal shape. Okay, so here, exactly the same, but the velocity of the counter-propagating curling are faster than the velocity of the radial growth. And then, well, what you have is the curling, the self-curling of the 2 counter-propagating curls, okay? And this here is what we call worm-like structure, formed when one of the curls have a radius curvature much higher than the other one, so it curls on itself. And this is a shape. Okay, so this simple mechanism explains you that by this mechanism you can have many different shapes that look like biological, right? But it's not biological, you can see at all. So it's actually not life involved and no organic compound involved. This is pure silica. This is why, this mechanism could apply to forms produced, during the early years in this planet when life was not even yet even appeared on Earth, right? So this is the chemical driving force. How much time you have?
15 minutes.
Plus discussion, right? Maybe. Okay, I will go very fast here. Okay. No. It's okay. No, I prefer discussion much better later. So this is why I want to have at least 20 minutes for discussion. Okay. The chemistry of this, because I think this is interesting. This is the solubility of silica as a function of pH. This is the key point here. About pH 8.3, the solubility increased dramatically because of the formation of the first and second deprotonation of the silicic acid, right? So this is here is a very large variation of pH, of solubility with pH. So what happened in our opinion is that when you provoke the precipitation of the carbonate, the pH decrease. Imagine that you are forming, this material is growing, okay? And then in the grow from, you have the precipitation of the carbonate, the forming crystal of carbonate. But what happens is that the crystal carbonates just start to form, you have a decrease of the pH, and decrease of the pH provokes the precipitation of silica, right? Because we have here in which the first derivative is very high. So the small decrease in pH provokes the precipitation of silica. So the precipitation of silica inhibits the growth of the carbonate forming crystal, so that they start as a nanocrystal, they cannot grow further, okay? But the precipitation of silica, well, increase the pH. And increase the pH, right? What happens is that then provoke the precipitation of carbonate again. So this is a self-coupling mechanism, okay, that produce a variation of pH in the grow from, okay? And this is the mechanism that is able to have this complex morphology, you know, because this is something that you can provide. Many people do is just to include a polymeric impurity with a crystalline phase, so that you could provoke the fractal branching, right? But the point is that in this case, the impurity is provoking the formation of the crystalline phase, and the crystalline phase is provoking the formation of the impurity. So you have a self-feeding mechanism, and this self-feeding mechanism, in our opinion, account for this, the formation of this biomorphic structure. So, well, this is this is the model, you know, that we have used in order to explain that everything happened in the grow from. So we have the idea, I think that we have here. Yes, we have a proof of the localness of the growth process. So what we think is that the bulk, what happened in the bulk is not interesting here. What is interesting, what happened exactly in the growth from, okay? Why we say that is because if you may perform this experiment with 300 revolutions per minute of stirring, still you have the formation of these shapes, okay? And remember, these are self-assembled nanocrystal. So everything depends on the kind of forces, physical forces, that induce the nanocrystal to self-co-oriented one each other, okay? So we think that what really happened, interesting is what happened in the internal, no, in the grow from, okay? So what we show here is that when you solve the chemistry of the precipitation, of the coupling of the two precipitation, the silica and carbonate, okay, you had really a maximum, I mean, the possibility to have this kind of structure only in the pH range, in the pH window that actually we observe this phenomenon, okay? So the problem is that we submitted this paper, and the referee say, okay, this is very good, but you have to show. I mean, and then the point is how to measure the pH, right? How to measure the pH here. So we did it with a colleague from Bologna using a fluorescent microscopy. I will go faster on this because the point is basically is that this fluorescent, this is a wonderful technology, so that really you can have you can find and measure the variation of pH locally in few micron, right? And with a very fast and with a precision of pH very high. So we followed. It was very difficult to obtain this kind of video because we should avoid any complex shape, right? That will kill the measurement, right? So we have this. Let me just show again. This is a growth rate. This radial growth, okay, is before any curling. And then we measure the pH. So you can see that really the pH change only in the grow from, not in the bulk, right? And by measuring the pH, I mean the intensity of the pH around this, okay, we can see that you can see the distance, I mean the in from of time, this is the growth rate, right? But distance in from of time, you can see that there is a variation. This is the scale of the code of pH. You have a variation of pH in time, you know, a oscillation of the pH value during the growth of the crystal, right? So we think that this is a proof that actually what we have is an oscillation of pH in the growth from that driving the formation of the carbonate and the incorporation of silica, right? And this do not necessarily mean that you should have oscillation or a banding structure, not necessarily. So the important thing is that because of this mechanism, you have the formation of the carbonate and the precipitation of silica, right? And this precipitation of silica is the one who inhibits the further growth of the carbonate so that you can have a nanocrystalline material self-assembly continuous growing, okay? So as I told you, this is only good for carbonate minerals. This is something that one of my students, Gansan, is made and discovered recently. This is under certain conditions you can have the formation of calcium carbonate, okay, and you have the polymorphic formation of the two, I mean, calcite and aragonite. And interestingly, calcite, as I told you, never form this complex structure, only dendritic growth, okay, only dendritic growth, while aragonite produce the complex morphology. So this is what happens, is that you can really identify aragonite calcite just by looking the morphology. Actually, this is, you can see that very close. Oh, I don't have here. Oh, it's a pity I don't have here. But you know, this is very interesting because you can have in the same tube, you can have first the formation of calcite, this dendritic growth here, okay, and then the formation of aragonite with this complex morphology, and again the formation of calcite. So it's a proof that the complexity depends, in my opinion, not on the crystal structure, but on the crystal shape of the nanocrystal forming the calcite. So these are, I would like to, this is just, Carling is a very interesting mechanism because it's morphogenetically it's very powerful, but as far as I know, I was talking with many biologists and life never used this mechanism. And I wonder because this is really very powerful mechanism. So just to go back to the early part of this talk, you know, remember that morphology does not contain genetic information. This is just to show you, this is my biomorph, you know, but this is a similar structure, you know, exactly the similar structure that some of the picture I showed you before, but this is provoked by injecting a jet, okay, a solution on a glass, okay? So you cannot really distinguish between, actually, you look for the detailed geometrical properties of this structure and biomorph, there's no different. But the mechanism formation is completely different. Okay, again, I mean, morphology does contain genetic information. Right? We cannot really rely on morphology. And then the problem of primitive light detection, I mean, why this is relevant? Because in principle, well, you know, this complex morphology could be just a curiosity. You know, why silica biomorph should be related with this problem of light detection? Because, you know, I was looking in my archives and you can really found, you know, morphology was very, even this morphology, which is very complex, you know, you can see that this is a biomorph, this is the Western Bargoon. I don't say that the Western Bargoon is not a fossil. I mean, I'm not saying that. I'm not saying that. I say that we need to have additional information to be sure. Okay, I say that this because complexity is not enough to be sure about the biogenicity. So, as you know, silica carbonate mimic very well, but remember that to be relevant for the problem of light detection, they had to fulfill two conditions. Must be the result of several sample processes. This is well fulfilled because it's actually self-organized material, but they must be geochemically plausible. And in my opinion, this is not a problem because all the putative Precambrian microfossils have been found in chairs. Chair is silica, as you know very well. And silica gels and silica, you know, in the Archean time, well, there are very many different ways to precipitate silica. One of the ways is actually to have an alkaline silica solution and a chain of pH. A small chain of pH will precipitate silica. So in principle, this is something that it is geochemically plausible. In addition, you know, the oldest putative microfossil published are found in barytic shale. So barium was available in the early planets easily, and silica for sure. You know, there was plenty of silica in the early planets. We can talk later if you, during the discussion, you like more about this. But this is geochemically plausible. So it's not crazy to say, well, you know, be careful because I think that we can have in chairs reaction leading to the formation of this biomimetical material, okay? Actually, when we look for this Roger Buick criteria for microfossil recognition, I mean, all the criteria were fulfilled by biomorph. Even it was not in the very beginning the composition of kerogen, but this is something that we made with my colleagues Stephen High. And then what we use is, well, there was, now it's well known that by the, heating siderite, you can create very simple organic compounds. And these organic compounds, you know, we know that was really available in the early days of the planet. So we take this simple compound, organic compound, we pour in the solution in which we grew the biomorph of silica, and then we heat to 350 degrees, and then we remove the structure in which certainly all the organic compound were to the silica, but it's something that was expected. You know, silica is a trap for organic compounds. And then we made the Raman spectroscopy, and exactly then the Raman spectroscopy of the found in the microfossil recovered from the early rocks, right? So this is something that not only the morphology, even the chemistry, the carbonaceous chemistry, can be really produced by silica biomorph. Well, this is the main message, as I told you from the very beginning of the talk. The morphology does not contain inequivocal genetic information. This is the key point, all right? So these are actually silica biomorph. You know? So the point is that when we can start to use morphology as a criteria for life detection, in my opinion, you know, when the complexity is enough to have comparative anatomy, okay? But certainly, when biology defeats physics, because at the very beginning, you will have just a two-dimensional membrane, okay, made by lipids or made by silica, okay? You have the two-dimensional membrane, and then you have, in biology or in organic compound, you will have osmotic force, anisotropy, you know, physical parameter, I mean, the resistance, so pure physics, okay? So the only way to start using morphology as a criterion for biogenicity is to, when Darwinian process start to be working, okay? When biology defeats physics. At that moment, okay, I think that we can start using morphology. Before that, I think it's impossible to distinguish the output of the physical processes and the output of the biological process, because the biology will basically shape the organisms at the very beginning with physics and chemistry. Okay. So higher pH, well, what happens at higher pH is rather than to have a carbonate, you have the formation of hydroxide. This is what people know from many years ago, silica garden or chemical garden. Okay, this is the what happened. You have imagine you have a iron 3 or iron 2 salt inside a glass, and you put the silica solution. Okay, and then you have a membrane of silica metal silicate hydrate. You know, that behave that way. So you have a phenomenon that is mimicked very well, and many people, you know, when look this, immediately consider this is related with biology and maybe related with origin of life. There is seen 19th century people thinking that this is a way related with the origin of life, maybe, right? But not because of the morphology. I think we have to apply here the same thing. I mean, there's something that look inorganic, that look like biology. Okay, it's not necessarily related with the origin of life. Okay, so but I think I have 2 minutes. I will just tell you the most important thing. This is also very biological. It's interesting also for well, this is more related with other things. But just in the context of this talk, I think that what's really interesting is that you can have this kind of material in geochemical environment. Okay, this is an experiment in which we took a solution high pH 13, you know, solution with some calcium inside, and then we pass the solution through a granitic rock. Okay, when you have the solution this granitic rock, high pH solution this granitic rock, you provoke the dissolution of plagioclase and quartz, and you form these tubes. Okay, these tubes form in granite. Okay, so if you look for the formation of this tube, this is what we call reverse chemical garden. Okay, that look like tubular shapes, that look very biological. So this experiment tell us that it is possible to have this chemical garden, you know, formed in geochemical environment. Actually, this is a geochemical environment. Okay, and this is the explanation for the formation of these tubes. Okay, this tube I told you here. Okay, this is not biological. This is clearly related to the process called a chemical garden. I think a reverse chemical garden. And I was reading this paper. I think that you published this paper. This is very interesting paper, very well, and a study very precise and with the last technology. And you demonstrate here that this kind of structure, this is 50 microns. Okay, this kind of structure are not really, that look like biological, are not really biological, right? This is you show that because of many different, it's a very complete, a very dedicated study. You know, it's very well done, and there are several reasons why this doesn't like, it cannot be considered to be biological. You know, but could be. You know, this could be related also to silica garden. This could be another alternative explanation, because this is actually what happened in Portland cement paste, which is the chemistry of similar to the chemistry of the and so this will be very interesting. I mean, maybe this week we can talk about if it is possible, because the morphology is very similar. The process, I mean, it's in chair, it's also in gels, in silica, in silica-rich solution. So maybe it's a task to this week to talk about the origin of this structure. Okay, thank you very much for your attention.